Good afternoon, ladies and gentlemen. I'm Samuel Estala Arias, and I will present an abstract of my work entitled Distribution of cross-sections in the Hilbert modular orbifold. I realized this work as a PhD student in the Universidad Nacional Autónoma de México. I have divided this presentation in 4 steps, beginning with an abstract, then settings, main results, and the case of the classical modular orbifold. We begin with the abstract. Let K be a number field or an algebraic number field. Let M be the Hilbert modular orbifold of this algebraic number field. And let MQ be the probability measure uniformly supported on the cross sections of the Hilbert modular orbifold at high Q. We generalize a method of Xavier and show that MQ distributes uniformly with respect to the normalized hyperbolic measure M on the Hilbert modular orbifold as Q tends to 0, and relate the rate by which MQ approaches M to the Riemann hypothesis for the Dedekind zeta function of the algebraic number field K. So the settings begins with an algebraic number field of degree n. We write the degree as R1 plus 2R2, where R1 is the number of real places and R2 is the number of complex places. We also have a ring of integers and a Riemannian manifold or symmetric space H formed by the product of R1 hyperbolic planes and R2 hyperbolic spaces. We also have the Hilbert modular group, which acts properly and discontinuously on the symmetric space H by a formula related to the Mobius transformation. If the field K has class number H, then the Hilbert modular orbifold, which is this quotient space, has H cost, and each cost can be parameterized by the standard cost at infinity. So we have a picture like this one, which is a manifold with a finite number of ends or cost, and from the geometry of the Hilbert modular orbifold, each cost has a parameter, one parameter submanifolds of codimension 1, which can be think as a generalized closed orosphere. And in these manifolds, we can define probability measures that are uniformly supported on the cross sections when we think that the transversal sections have associated a Riemannian metric that is inherited from the ambient space. We sum up the H probability measures and normalize it to have a probability measure, and we also consider the normalized hyperbolic measure of the Hilbert modular orbifold. The main result of this work is the following. Let M be a smooth function of M with compact support. Then we have the following relation, which in particular tells us that the measures MQ are uniformly distributed with respect to M as Q tends to 0. And therefore we have a picture like this one. We have here submanifolds of codimension 1 that start to cover the whole Hilbert modular orbifold. We also give a generalization of Xavier's equivalence to the Riemann hypothesis and prove the following assertion. The Riemann hypothesis for the Dedekind zeta function of K holds if and only if for every smooth function f with compact support on the Hilbert modular orbifold, one has the following relation. So the rate of approach of the measures MQ can be better if and only if the Riemann hypothesis for the Dedekind zeta function is true. Finally, we will present the example of the classical modular orbifold, which is a theorem due to Donsaghier. Here we have the Dedekind tessellation of the hyperbolic plane and the classical modular orbifold. The classical modular orbifold has a one-parameter family of closed autocycles. Here we have one closed autocycle and another one which is of bigger length. We see that it starts to cover the modular orbifold. Finally, when the length of the autocycle increases, it starts to cover the modular orbifold uniformly. This is related to the Riemann hypothesis, which is also related to the prime numbers, and I have pictured here the prime numbers using the Maya numbers. We highly recommend a video which shows a simulation in the case of the hyperbolic plane. Finally, we also want to thank Professor Alberto Verhovsky-Solá for suggesting Saghier's equidistribution theorem in the Hilbert modular orbifold and for all his great explanation on this remarkable subject. I'm Samuel Estala Arias. Thank you very much. See you later.